Bismillahirrahmanirrahim. Now we will again go through this dependent and independent and mutual exclusive things again a bit more in detail, because the concept should be clear. What is independent event and what is a mutually exclusive event, and what is the difference between the two. So first, we look at conditional probability. Suppose there are two events A and B. If the two events are related, then probability of event A depends on event B or vice versa. To find the probability of occurrence of event A given that event B has occurred is called the conditional probability. So actually we have seen this conditional probability before, but we did not use the term conditional probability. Here actually it is just the matter of dependence. So the event A depends on event B, and in that case the probability is calculated probability of A intersection B divided by probability of B, and we have actually okay. So dependent events again, we have talked about it earlier. Now we talk about it a little bit more in detail over here again using tree diagram. This example is taken from Math is Fun website. It's a very good example. So you can to go more in detail and other stuff related to this topic, you can visit this website over here, www.mathisfun.com, and the link is given over here. So suppose that we have got a bag, and in that bag you have got 2 blue and 3 red marbles. As you can see over here, there are 2 blue marbles and 3 red marbles, and altogether you have got 5 marbles. What are the chances of selecting a blue marble? So in the first time, here you are going to select a marble, and you are going to determine what is the probability of determining and getting a blue marble. So it's very simple. 2 divided by 5, this is the chance of getting blue marble. And if you say what is the chance of getting red marble, then it is 3 divided by 5. But after taking one out, the chance changes. Why? Because we are talking about without replacement. Once you have taken out a ball, you're not going to replace it in the bag again. So for example, in the first selection we got a red marble. So if in this case, if I have selected red marble, then the chance of selecting a blue marble is 2 in 4, because I am not going to replace the marble. So total number of marbles has reduced to 4 from 5, and the total number of blue marbles is 2. So the probability of getting blue marble in the second selection is 2 divided by 4, or 2 in 4. But if we selected a blue marble in the first selection, then the chance of a blue marble in the second selection is 1 in 4. Here you can see that again the total number of marbles is the same, 4. It has been reduced from 5 to 4. But now since you selected blue marble in the first draw, so in the second draw the chances of getting blue marble is 1 by 4, because only one blue marble is left in the bag. So if we draw a tree diagram for probabilities, then we say for first time, for our first draw, then the chances of getting blue marble is 2 by 5, because you have got 2 marbles in the bag and you have got altogether 5 marbles. So 2 by 5 is the chance to get the blue marble, and 3 by 5 to get the red marble, because there are 3 marbles. But once you have drawn either a red marble or blue marble, the number of marbles have reduced. Now here you have got 5 marbles, and in the second draw you have got only 4 marbles. So out of 4 marbles, if you got blue marble in the first draw, then only one blue marble is left over here. So in the second draw, the chance to get blue marble is 1 by 4. and to get red marble is 3 by 4. And in the if you got red marble in the first draw, then in second draw there are only 2 red marbles left. So to get blue marble is 2 by 4, and to get blue marble is also red marble is also 2 by 4. So here you can see that if you had drawn red marble, then the chance to get blue marble and red marble in the second draw becomes equal, 50-50%, 2 by 4, 2 by 4. But here the chances are different. So in this because it is without replacement, so the second draw depends on the first draw. So we call them dependent events. So let getting blue marble in the first draw be event A, and getting blue marble in the second draw be event B. We are talking about 2 events. The first event is that did I get blue marble in the first draw, and the second event I am observing whether I got blue marble in the second draw. So in the first draw, as we know that to get the blue marble is 2 by 5. That is fixed because it doesn't matter whether it is the first draw. So it is independent. It only depends on the number of blue marbles in the bag. So it is 2 by 5. But in second draw, as we have shown over here, in second draw, if you got blue marble in the first draw, then to get the blue marble in the second draw is 1 by 4. Here you can see. And if you got red marble in the first draw, then in that case the chance to get blue marble is 2 by 4. So the probability of event B depends on probability of event A. So we have to say which one we want and use the symbol pipe as we have discussed earlier in the early videos as well, which means given that or given or such that. So B given A means event B given event A. And what is the probability of event B depends on the probability of event A, and whether event A has occurred or not, it depends. In other words, event A has already happened. Now what is the chance of event B? So probability of B is probability of B if event A has occurred is 1 by 4. Means if the blue marble was selected or blue marble was drawn, in that case the probability that of event B is 1 by 4. But if blue marble was not drawn in the first selection, then the probability changes to 2 by 4. Probability of both the events A and B to occur is P intersection B. We know that n means multiplication in probability, hence the probability of A multiplied by probability of B given A. As you can see this here, this one is actually P probability of B given A. So here what the outcome or the total probability is simply multiply this probability by this probability. So this probability is nothing but probability of A multiplied by probability of B given A. So we have multiplied probability of A by probability of B given A, and if we just use this simple mathematical operations, we get probability of B given A is equal to probability of A intersection B divided by probability of A. And similarly, if your event A depends on B, in that case probability of A intersection B is divided by probability of B. The point to be noted is that if we replace the marbles in the bag each time, then the chances do not change and the events are independent. So with replacement the events are independent, without replacement the events are dependent. So now we look at the difference between mutually exclusive and independent events. If two events are mutually exclusive, then P intersection B is 0. Means since they are mutually exclusive, they have got no relationship at all. So if you try to find the intersection or anything common between these two events, then we will get 0. And in that case, the union of those two events is simply adding the probability of each event. Probability of A plus probability of B gives you probability of A union B. If two events are independent, then the intersection of these two events is simply multiplication and of A and B, and union of probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. We have seen about this in previous videos, and we have discussed this thing in detail. So probability of A intersection is equal to 0 means that mutually exclusive events cannot occur simultaneously, like flipping a coin. So if you get head, you cannot get tail. If you get tail, you cannot get head. So these two events are mutually exclusive. And probability of A intersection B is probability of A multiplied by probability of B, means that events are independent but may occur simultaneously. Female, so let's have a look at this table. We have got female and male, and there are 50 female engineers, 75 female doctors, and 80 female accountants. Altogether we have got 205 females, and we have got 70 male engineers, 60 male doctors, 65 male accountants, and altogether 195 males. So total we have got 400 persons, and total number of engineers is 120, total number of doctors is 135, and total number of accountants is 145. So now we will see which events are independent and which events are mutually exclusive. So the probability of being engineer is 120 divided by 400 is equal to 0.3, because total number of engineers is 120. So 120 divided by total number of persons divided is equal to 0.3. Probability being a female is simply total number of females divided by 400 is equal to 0.5125, and being engineer and female both is simply this one 50, because this one this is the number of female engineers. So it is 50 divided by 400, 0.125. Now the union of engineer and female means that either your engineer that person is an engineer or a female is equal to P engineer union female is equal to P engineer plus P female, as P engineer plus probability of female, and then subtract the intersection, which is probability of engineer intersection female. So we have calculated these values above already. We just put it over here and we get 0.6875. But now when we look at probability of being engineer and doctor both, as we know that either a person can be an engineer or a doctor, it cannot be both. So these two events, being an engineer and being a doctor, are mutually exclusive. These two events are mutually exclusive, so the probability is 0. And probability of being engineer or doctor, because here again they are mutually exclusive, then we simply add up the probability of being engineer and probability of being doctor, and we get it is 0.63675. There is another example of conditional probability. A chip manufacturing factory produces good and bad microchips. The lifetime of a good chip decreases exponentially with rate of failure alpha. So that is e raised to power minus alpha t. After it exceeds time t, and failure rate for bad chip is 1000 alpha. So e is raised to power minus 1000 alpha t. Suppose the probability of bad chips is p and good chips is 1 minus p. Find the probability that a randomly selected chip is still functioning after t seconds. So let's see the event chip still functioning after t seconds. The event is chip still functioning after t seconds, and let G be the event chip is good and B the event chip is bad. So we have got three events: chip is good, that is event G; chip is bad, that is event B; and chip is still functioning after t seconds, that is event C. We have to find the total probability of both the good chip and the bad chip because the problem says randomly selected chip. The lifetime of the selected chip depends on its type. If good chip is selected, then the probability of lifetime is e minus alpha t, and for bad chip it is e minus 1000 alpha t. So therefore probability of C intersection G, probability of C, chip is still functioning after t seconds and chip is good as well. That is probability of C given that good chip was selected multiplied by probability of G. So we know that probability of C given G, it is given in the question over here, that it is e minus alpha t. So e minus alpha t multiplied by 1 minus p. And probability that the chip is still functioning after t seconds, given that we have selected bad chip, it is e minus 1000 alpha t into p. So the total probability is nothing but we add up these two conditional probabilities and we get e minus alpha t 1 minus p plus e minus 1000 alpha t p.